Thank you. So yeah, today I'll be talking about embedded. It's probably going to be more about embedded than actual game design, but it is game themed, so hopefully it's still applicable. So I titled my talk "Games but No Video," and that's because when we talk about game dev, we usually assume that it's on a computer or a console or mobile, something that has a screen and has like regular input methods. But there's also other types of games that you can use Rust for, and I made one of those, so let's go through it. I've been sort of making games since I was 11. Haven't released a commercial game. Maybe in another 10 years I'll be able to. I've been writing Rust for over 5 years now, I think 6 or 7 coming up. And about a year ago, I started professionally working as an embedded developer. And I've been doing sort of embedded as a hobby, sort of passively for a couple of years. But now that I'm doing professional stuff, I kind of wanted to learn more about the actual hardware side of things. So I know the software fairly okay, but I don't have any sort of formal education about electronics, just like high school physics class. How does electricity in general work? So I wanted to learn more about that. So I needed a project, and I definitely wanted to keep it very simple. I didn't want to go over my head and have like a 3-year-long project. And also, I very much subscribe to the idea that constraints sort of help you bring out your creativity when designing, especially games. So I wanted to give myself a really, really tight like hardware side and see what I can make. And for context, I wanted to make something like on the level of complexity of like what you would get from McDonald's as part of your Happy Meal. So like a little game trinket. And that was, if you know a little bit about mobile gaming history, the Game & Watch, which was in a way one of the first mobile gaming devices. It was invented by a guy from Nintendo who saw someone play with a calculator on their commute. And he figured, oh, that's kind of fun. That's like a thing you can do for 3 minutes when you wait for your bus. So I wanted to make one of those things that you can just pull out, play with for like 2-3 minutes and be done. So when developing embedded stuff, really the core of your system is going to be the microcontroller. Microcontroller is like your processor and sort of your motherboard and I/O in one small thing, one single chip. And you really have tons of choices where you go with this. There's really popular microcontroller brands. You got ESP32s, STM32s, at Mega, which is used in the Arduino, for example. And just tons. There's like 101 manufacturers, and all of them have 101 different product lines. So there's a lot of options. I wanted something small. So, for example, ESP32 was kind of out. It has hundreds of kilobytes of memory, and it can do Wi-Fi and Bluetooth. So it's kind of overkill for what I needed. And most of these chips also run some variant of the ARM instruction set, which is great because it lets us use common ARM toolchains. Rust supports ARM pretty well. And then some of the smaller, like, for example, the ATtiny, which is a really small chip. It uses a less common instruction set architecture, which makes running Rust a little bit trickier. There are some forks that support ATtinys, but it's not official support. And there's a sort of new instruction set architecture that came out a couple of years ago called RISC-V. And it's notable because it's free, it's open source. So any manufacturer can sort of implement it, and they don't have to pay any like licensing costs to ARM or anyone else to produce chips that have like wide tool chain support. And one of these chips that got really popular last year is called the WinChip Head CH32V003, which is quite a mouthful, but that's how almost all microcontrollers are. And it got really popular last year in like the maker community because it's really cheap. It's really cheap. You can buy it. It comes in a couple of different packages. So like the chip inside is the same, but they have different form factors. And some of the smaller packages, they go down to under 10 cents a piece, which is really cheap. So I think I picked this chip because it looked cool. It was RISC-V. It was simple. It was really cheap. And yeah, in general, it has 2 kilobytes of RAM, which is, if your computer these days has 2 gigabytes of RAM, it's very small. This has 1 million times less, but it's still tons for developing simple games. 16 kilobytes of read-only memory, so that's where your actual program code lives in. And you can get it, depending on the package, you can get it with either 6, I think 12 or 18 like input pins or general purpose input output pins. It has a bunch of other stuff. It has like serial buses, which let it communicate with other things in your embedded system, like I2C, SPI. It has analog converters, but something that really caught my eye was that it supports power sources that are from 3 volts to 5 volts, which is good because I wanted to run my embedded stuff on these regular like 3-volt coin cell batteries. But also I wanted to have the option to make like a rechargeable lithium polymer battery, which those batteries have a voltage of 4.2 volts at maximum. So because this chip supports anything from 3 to 5 volts, I could use any sort of power source I wanted without any external components. So we picked this even longer name, V003 J4M6. The J4M6 just means it's packaged in a SOP 8 package, which is an 8-pin sort of thing. You can see it on the left. And 2 of those pins are used for power and ground. So you only really get 6 general purpose input outputs. Okay, what can we do with those inputs? That's not a lot if you think about it. I mean, a mouse, a regular computer mouse, has way more data you can get from it. Like, of course, you got 2 bits for the main click, but then the movement, that's 8, 16, 32 bits. And like a single pixel on a modern monitor has 24 bits of output. So what can we do with 6 bits of combined input output? We could sort of cheat, and we could use, for example, for the output portion, we could use, for example, displays. I think I have, yeah, here's a little OLED display that only needs 4 pins, 2 pins and then 2 pins for power and ground. But you're sort of moving the responsibility elsewhere, so it's not really, it's kind of cheating. It doesn't follow keep it simple. So I only wanted to use simple like LEDs and buttons that map like 1-to-1 pin to input or output. Okay, we can do a little bit of cheating. There's a technique called Charlie plexing, which lets us drive more than N LEDs from N pins. I'll skim over it very quickly, but yeah, this hardware really put those limitations tight on me. How can you make an interesting game that will keep you occupied for at least 5 minutes with just 6 inputs and outputs? Well, because all the inputs and outputs are digital. First thing that came to my mind was something to do with bits, and I started prototyping. I used MacroQuad. It's really helpful. I made my first prototype in like 5 minutes. It's just showing a bit pattern, and then you had a couple of buttons that you could press that would perform like a bit operation on that random bit string. And the goal was to like get all of them to 0 or get all of them to 1. It was okay. It didn't work super well, but after some iteration, I came up with a game that was about having 2 6-bit integers, and then you keep adding them to each other until you get them all to be all ones. And that actually ended up being pretty okay. I liked it. That sort of game requires 2 button inputs, so that uses 2 of our 6 pins, leaves 4 for our LEDs. But Charlie plexing, like I said, it's a technique that lets us sort of exploit the nature of these GPIO pins. So instead of being just pure on-off, like binary, these pins are actually tri-state logic. So what that means, each of these pins on a microcontroller can either output like high voltage or low voltage to control, for example, an LED. If it outputs high, then LED comes on. But you can also set it to an input state where it's called a floating Z, where it basically acts like nothing is connected to that pin. And if you wire up your LEDs in a certain way, you can wire up to like N pins. You can get actually way more controllable LEDs out of it. You can't light them all on at the same time, but if you sort of flicker through them fast enough, you can control quite a bit of LEDs. So with those 4 remaining pins I was able to control 12 LEDs, which is actually perfect because we had two 6-bit numbers, and 12 LEDs enough to sort of represent that. I also made a simulator of that. It's on the bottom there. Made it in JavaScript. It took me like another 5 minutes, and played around with that. Figured, okay, this is good. So let's make some hardware. Took me a while to learn about how to actually make PCBs. Wasn't the greatest PCB ever made, but it works, which is good enough for me. There's a couple of designs I made for it. The sort of middle one is what what's like the final revision. There was also the bottom one, which wasn't as ergonomic to use. Yeah, and the actual game logic ended up being really simple. So you have these 6 LEDs here at the top and a button next to it, and another 6 and a button on the bottom. Those are your 2 numbers represented by the LEDs. And when you press a button, it adds sort of like the other number to the one you just pressed. And if all of the bits in both of the numbers are on, then you win. That was really the hardware part of this. I will show you. Here it is in real life. Got these manufactured, took a couple of weeks to ship, but I have one in my hand. This camera, of course, does not focus, but I'll show you a video later on. Looks like this. On the flip side, there's a little Ferris. Now that we have the hardware down, let's get to Rust. So Rust already supports RISC-V, which is great, but RISC-V is sort of a modular architecture. You have what's called a base instruction set, which has very simple things. It has integer addition, branching, a couple of bit operations, and then you add on these like features that allow it to do more things. For example, you can add a floating point unit, and then it becomes an RV32IF, and the F means that it has floating point support. This microcontroller itself, it's an EC part. EC or C means that it has compressed instructions, which helps keep the code size small. But the E is actually a bit tricky because it's not technically part of the RISC-V specification yet, so not all compilers support it. And the E is like a smaller version of the regular instruction set, which only has 16 registers. Normally, RISC-V has 32 registers, but with the E, you only get 16, and it saves a bit of space on the actual hardware die. Okay, Rust doesn't support the E extension because it's not official. It's not ratified yet. It's not a big change. It's only just reducing the number of registers, and with that, sort of tweaking the ABI so it works. Luckily, someone has already done this for us. Some person, I think from a company called T-Head, has made a patch to LLVM that supports the RV32E instruction set. So it was really just a matter of bringing in that patch, applying on top of Rust's version of LLVM, which was quite a painful merge. LLVM moves really fast. I think I was late by like 14,000 commits or something like that. But after a couple of hours of merging, I got it working, and we have proper code generation for our chip. Okay, now what? To sort of get our LEDs and buttons working, we need to do some hardware access. So of course, because we're writing embedded, there's no STD. You can't just like write out. It's not, Rust doesn't know what it's running on, so it can't include anything out of the box. So we only have core. And to sort of access, for example, how do you set one of the pins on this microcontroller on? You have to do it through something called memory mapped IO, which is just a specific memory address in the 32-bit address space that when you write to it or read from it, that causes actual things to happen in hardware. And there's like thousands of these memory registers, even on these small chips. And they're all documented in what's called a technical reference manual. For this chip, because this chip is very bottom of the barrel, really cheap. It doesn't have many peripherals or hardware functions, but it's still almost 200 pages. But if you look at the reference manual and you write it out, you can use, for example, raw pointers to write your values directly into the sort of magical memory addresses, and it works. That's how I got my first LED blinking, but it's not particularly pretty, and I definitely wouldn't want to do this for all of the thousands of different registers that you have. Vendors kind of, so like chip vendors know this. It's really painful to program for these, so they came up with something called SVD, which is a system view descriptor file. It's an XML file that describes all of these registers that a chip might have. And then there's tooling for Rust. There's SVD to Rust, which can look at the XML file and generate a crate for you that sort of abstracts over this raw register access. And it looks sort of like this. So you have singletons. You have the peripheral singleton that you can only take ownership of once. And then using the members of that structure, you can modify individual bits in all of the registers. And it sort of makes sure that you don't like typo an address or write a wrong bit pattern to something that doesn't support it. Okay, and packs really help writing code. I mean, this what you see on the bottom is much easier to reason with than actual just raw memory addresses. So with that, I got my first version of this game working. So you can see there's some debug wires running to the board, and it has LEDs on it. And it was great. It worked. But we can do even better. So instead of writing, even though it's a bit of a nicer API, we still don't want to manually deal with the hardware. Rust has a great ecosystem for this. There's a crate called Embedded HAL, which provides a lot of very high-level generic traits for controlling, for example, pins or serial buses or other peripherals. Then that sort of lets application or like firmware programmers do not really care what hardware they're writing on. So you can reuse code between different variants of a chip or entirely different chips. It all works together, and it's a safe API. For that, you need what's called like a chip-specific hardware abstraction layer, which implements those traits on top of the peripheral access crate that you just generated. And with that, now the sort of API for setting a pin on looks more like this. So you have, again, you have the peripheral singleton, but now you can turn it into a sort of higher level, strongly typed pin that's configured into, output pin, and then you can safely write different states to it without dealing with any registers or any hardware specific stuff. And once you get that working, here's a little recording of me playing the game. So you press a button, turns on, it gives you 2 random numbers, and then, okay, here you can cycle the LED brightness between 3 levels. And by pressing the different buttons, you add the other number. So here I was pressing B, and it added A to the B number. And okay, there you go. I just sort of finished it. That was an older firmware. Now, if you sort of beat the game, it flashes the LEDs, lets you know that you won. In this version, it just instantly randomizes the numbers again. Here you can see in A, I have 2, and I'm just adding it to B until B is fully lit. And then because how overflow works, you can sort of add 63, which was in B, into A, and it'll underflow back to, so that all the bits are 1. That's how it works. The actual sort of firmware that ends up running on this after all the packs and hardware abstraction layers is only about 300 lines. The gameplay itself is maybe 20 lines, but the majority of the code is still controlling all of the different LEDs according to what you have in A and B, the brightness controls, making sure that when you press a button, it doesn't register like buggily S2 presses. And majority of the code is actually about power management. So you can see if I don't press anything for a couple of seconds, it goes into sleep mode, which lets this single coin cell last for like weeks or months. It doesn't really use any energy that way. Most of this stuff is abstracted through like the HAL, so it uses the safe interfaces. But some behavior is really hard to describe in a safe manner, in a safe API. For example, the power management, this going to sleep, is really hard to make in a HAL because it has some implications. When you go into sleep, what it does, it pauses your program execution, but it also resets some of the peripherals. So for example, the GPIO stuff, it gets reset between sleep states, so you have to sort of reinitialize it. But that's really hard to sort of express in an API, that suddenly your like well-defined state is now, it could be anything. So you do have to cop out and use the more lower level unsafe register access sometimes, but it's not too bad. I mean, this is a simple firmware, so it's not too hard to like program or keep it in check mentally. And this works. This is a sort of complete, I say it's in production. I gave one of these to my sister and she's been happy with it. So I guess I can say I've released a hardware game. All of this stuff is open source, so including the hardware, it's on Open Source Hardware Lab. You can get the schematics and board files if you want to make some of your own. The firmware, that custom fork of Rust, and all the peripheral and hardware abstraction layers, they're all open source. You can go look at them. They might be a bit ugly, still very much under work, especially the HAL stuff. There's only me and a couple of other guys who've been on like a best effort basis improving the ecosystem, but it's there. It's enough to get started. And if you want to learn more about sort of way more in detail about what it takes to actually patch Rust or generate those access crates or deal with, for example, I didn't talk anything about linking and configuring that sort of stuff. I have a blog post series I wrote this spring while I was working on this game. You can go read it. It's on my site. It's about, I think it takes like 45 minutes to read all the way through. It's pretty good. So yeah, that's this project done. I'm actually pretty happy with it. It ended up being sort of exactly what I expected. And now that I have all of the ecosystem parts done, if I want to make another one, design a different sort of game, it's going to be so much faster. I don't have to do all of this. I mean, I thought this was going to take maybe a week from start to finish. It ended up taking like 4 months, mostly because of all the hardware HAL stuff. So yeah, and now that we have these generic traits, we have the embedded HAL implementation. We get to use very generic drivers. So for example, in this picture, there's one of those OLED screens, and I didn't have to write a single line of code to get that working. Rust's sort of genericness really helps there. If I want to make, for example, I mentioned Tamagotchi earlier, I might do a project like that. and I want to use one of these displays on it, I don't have to write any like driver firmware for the display itself, because you get that for free with Rust ecosystem. So yeah, there's a lot of ways you can take these chips, even though they're very, very small and dinky, 2 kilobytes of memory. They can do it quite a lot, and I'm excited to see what sort of other games I can make. And I definitely learned a lot more than I thought I would making this project. Yeah, and I'm a good 10 minutes over my time. That's everything.
All right, perfect. So yeah, this was super cool. And so I'm very much going down the path of where you seem to be at the beginning of this. And so I'm very happy that like I have your resources now to go and check out when I want to learn how to patch Rust-C for whatever hardware I'm doing. But a few things I'm wondering about. And so with the chip that you used, so I'm using like the ESP32s. I've got like a few of them on like the real kind of thing, and then I've got like the dev boards as well. Yeah, it's like so fun having like these like little things that you can just plug into, and most of them run Rust right off the bat. But when it comes to the chip that you used, how constrained did you feel with what you were doing? Like, did you only use part of the available resources, or do you feel like you're really pushing up against the edge of what's available?
Not with this thing. This project, it didn't end up using that much. I think I allocated like, 100 bytes for the stack, and static variables take like another 100 bytes. So I'm using maybe 10% of the 2 kilobytes of RAM, and the firmware was, I think, about 2 kilobytes in total out of the 16K that I have available. But then some other stuff, for example, if you add the driver for this display, now it balloons up, and I'm up to like 12K, which is like, that doesn't leave much headroom. There's some things you can do to improve it. For example, this display, it has 8,000 1-bit pixels, so that it takes already 1 kilobyte of memory to store the frame buffer. But you can do some tricks. You can, for example, not store a frame buffer and generate it as you write it out to the display.
Oh, interesting.
You can do some tricks. I don't think Rust specifically adds like any bloat. So it's like the situation is as good as it would be with C or assembly. I didn't find a problem there.
And I guess like a question from that perspective as well, like when I'm doing stuff with higher level embedded Rust, so like I'm doing like, let's say like Linux on a Raspberry Pi or something, and I write out to SPI, I feel like, okay, I have this one function that is talking to the hardware, and now that I have that abstraction, I can use it everywhere, and it feels like I'm writing normal Rust. And so is that sort of what you experienced as well, or was it like, oh yeah, you had to be really low level the whole time?
Oh yeah, absolutely. Especially with the embedded HAL stuff, that already takes a massive load out of your brain, because you now just think in like the logical ways. But you can definitely separate the code out into like a very small shim that actually interfaces with the hardware, and you can use any Rust library really, and like write regular Rust.
Yeah. Okay. That's pretty cool.
You do have limitation. For example, you don't have an allocator. If you have a bigger chip, you can add your own allocator. But with 2 kilobytes of RAM, I didn't think allocation is really worth it.
Yeah.
But definitely on an ESP32, I've written Rust code that uses an allocator, and it really looks like regular STD Rust code for the most part.
Yeah, absolutely. And so when it comes to I guess like designing and like doing this iteration process, was it really like a sort of a linear process on this one? Like it was like so here's sort of what I heard when you said that you had to make changes to Rust-C, or you had like do his own version of stuff. Is like, to me, it would be like that there'd be a whole bunch of walls that you run into, and you have to figure out how to overcome, and you have to reach out to a lot of people and find out a lot of things. And so what was that process like?
Oh yeah, it was definitely, yeah. I thought it was going to take a week, 2 months in the end. So a lot of walls, mostly because with the Rust toolchain, I didn't sort of, when I ordered all the parts, I didn't realize it was an E variant of RISC-V. So I didn't know it was going to be a problem. But luckily, there's actually, there's a lot of way smarter people who do this a lot. And they're really helpful in the maker communities. Not very many people use Rust on this thing, but there's quite a few people that use regular C. and just talking to them really helped me with like how to control all the peripherals and what sort of quirks the code generation has and that sort of stuff.
Yeah. Okay. Yeah, this is super cool. So I saw that you have a blog post. I'll make sure to include it in like the notes afterwards. But I'm really excited to take a look through that because I think the process that I'm going through right now is very similar. And now that I have your resources, it's gonna be a lot easier. And so maybe in the future I will show off my own little project. My brother built this. My brother knows hardware and I don't know hardware as well, and so he like put together this like ESP breadboard kind of thing. And now I'm like, wait, maybe I should write a game on here. Actually, one question we have right here in chat, I guess relative to the discussion on sort of like handling some of these like overcoming some of these things. Is it easier to use Rust or C for that kind of stuff that you were doing? Did you find?
Okay, there's one very big difference. Is that all these vendors already provide C libraries and tool chains for you to do this sort of stuff. So you just get to the point with C. Once you have all the tooling in place, I prefer Rust. I like Rust. I like writing Rust. So maybe a project this small that doesn't really have very complex firmware in the first place. Rust doesn't give that much of a benefit. But I can imagine if you're building something bigger, if you're, for example, with an ESP, if you're writing like an IoT application that does Wi-Fi, then you really want that sort of Rust safety guarantees and nicer APIs. But to sort of get started, I think, C might be less friction.
Yeah. And then the question was also reposed from a different angle that I like quite a lot. So even though Rust has benefits, does it make the job harder by abstracting? And so were there times where you felt like you wanted to touch the hardware, but maybe like one of the abstractions that was there prevented you from doing what you felt should be natural?
Not really. Like, yeah, I can see what you mean, but I think with how peripheral access credits are handled, it's always sort of easy to just cop out and use unsafe and poke at the register manually. So you're not stuck with the higher level abstraction. You can always go in there and do it manually.
Okay.
So I don't think it was like a downside.
Sounds good. Okay, that makes sense. And then the final one here, which I also like. How many boards have you messed up because of bad soldering?
Do I dare to say? Let's see. I think I made 3 boards that I used for like development, and then I made 3 boards that I gave out to people. And out of those, I burned probably 2. So not too bad. I have some other boards that use the same chip, not the game boards, but like here's a little one that talks USB.
Here, wait, let's do this. Yeah. Oh wow, that's very small.
Yeah.
Interesting.
And I have these which are just breakouts. So this doesn't even have any hardware on it. It just breaks all the pins out. I burned quite a few of those last ones.
Yeah.
Mostly when doing like power management stuff.
Oh yeah.
Easy. But for the most part, these chips are surprisingly resilient. They definitely overexceed their sort of specification or what you would expect for a 10-cent part.
Okay, yeah, that's pretty nifty. My current goal is to basically make the exact same thing. So like design a PCB that's the exact same thing as like a development board, but it gets rid of all the fancy pins and stuff, and instead just has a whole bunch of lights that you can address. So seeing yours is like a pretty cool way to do that. And I also didn't. You mentioned a technique with being able to use one pin for multiple or a few pins for multiple lights. So I'll have to look into that. I think the Charlie is something.
Yeah, Charlie plexing. I presume invented by someone named Charlie. But yeah, it makes. Can I show? I have ECEDA open here. It doesn't generate very pretty schematics, but how do I get this open? I have. Let's see, slides, and then where is? There you go. So here's the sort of schematic for that board.
Really, this is it?
Yeah, here's the chip up here, and then you have the battery is over here. 2 buttons, and then here's the like Charlie plexing circuitry. So it's only using
a lot of D2s going to stuff. Oh.
So there's only 4 different pins going in, but depending on how you orient the LEDs, you can sort of trick it into driving more than just 4. It looks like this.
Okay. Oh, so cool.
Yeah.
Awesome. Oh yeah. Okay. So this is like the
Yeah, the
trace.
board file.
Huh. Yeah. Nice. Okay. Awesome. So we have a few more questions in the chat, but I'll let you answer them in the Rust Gamedev Discord. And so, yeah, I think there's be quite a lot of interest around some of the files and stuff. So I'll make sure that all the links are available, because I think it'd be pretty cool to check out. So yeah, thank you so much, Noxon, for going through that. I really like how we're like touching stuff that's like, it is game dev, but it's not like the classical game dev that we think of necessarily. And so it's very fun. Perfect. All right, and we will be back in just a minute to learn about Tunnit.